Hey everybody, Mr. Gibson here. So for this assignment, you are going to be exploring the inputs and outputs of cellular respiration and photosynthesis and how they relate to each other. Okay, so how are the inputs and outputs of photosynthesis and cellular respiration related? Like it says today, you're going to find out. So to begin this assignment, you're going to want to first open the attached Google Doc and complete part one, first and foremost. Okay, so let's open this up and take a look. It says, so this is part one. We got 1 through 6 here, a little chart, and then 7, 8, 9, 10. Okay, so let's go over this really quickly together so that I can make sure you guys are good to go for the other parts. So it says, what is the largest source of energy in an ecosystem? So where does energy enter an ecosystem? The largest source of energy actually comes from the sun. So the energy from the sun is absorbed in order to do photosynthesis, and that's how energy is captured and placed into an ecosystem. So number one, we're looking at the sun, right? Number two, why do organisms need a food source? So if you remember back from the last unit, we need food sources specifically that have carbon, hydrogen, and oxygen because we receive energy from those food sources in order to do cellular processes. We have to have food sources, things that contain glucose or things that contain other carbon, hydrogen, and oxygen molecules like lipids and proteins in order to use for cellular respiration to make ATP or energy in our bodies. Number three, what is the law of conservation of matter? It simply says that matter cannot be created or destroyed, or another way to phrase that might be mass cannot be created or destroyed. Number four, what is the balanced chemical equation for photosynthesis? So the chemical equation for photosynthesis is carbon dioxide plus water yields glucose, C6H12O6, plus oxygen. But if you were to count the atoms, the number of each type of atom on either side of that equation, you would notice that there's not the same number of carbon on the left side of that equation as there is on the right, or there's not the same number of oxygen on the reactants as there is in the products. And because of the law of conservation of matter, those atoms can't be created or destroyed. So what we have to do is write a balanced chemical equation to have the accurate number of each type of atom so that we have the same number of each atom in the reactants and the same number in the products, okay? So let me write that out for you to show you what I mean by that. Normally you would have CO2, and that would be a subscript. But for time's sake today, I'm going to leave it like that, plus H2O yields glucose, C6H12O6, plus oxygen O2, okay? But look over here, we've got 1 atom of carbon on our reactants and 6 atoms of carbon on the products, and so that doesn't obey the law of conservation of mass. So what we have to do is put numbers in front of these molecules to accurately reflect how many of each atom should be on the reactant side and the product side. And those big numbers are called coefficients, and this is how they work. So on this side of the equation, in the reactants, I only have 1 atom of carbon, but on this side I have 6 atoms of carbon. So how do I fix that? Well, I'm going to put a 6. Oops. I'm going to put a 6 right there. So now everything in front of that gets multiplied by 6. So I've got 6 carbons, 12 oxygens right here, and then another one over here. So that's 13 total oxygens, okay? All right, now let's look at our hydrogen. So over here we only have 2 H2O, 2 hydrogens, and over here we have 12. So what can I multiply by 2 to give me 12 hydrogens? Well, I can put a 6 there as well. Okay, so now over here on the left we have 6 times 2 is 12. 6 times 1 is 6. So altogether on the left side of our arrow, on the reactant side of the equation, we have 18 atoms of oxygen. Well, let's look over here on the right. We have 18 atoms of oxygen. We have 6 here and 2 here. That does not equal 18. So if I put a 6 right here, now we have 6 times 2 is 12, plus another 6 is 18. Our oxygens are also balanced. And so the way you would read this equation is the balanced chemical equation for photosynthesis is we have 6 molecules of carbon dioxide plus 6 molecules of water yields 1 molecule of glucose, C6H12O6, plus 6 molecules of oxygen. Okay, and now we have the same number of carbon, hydrogen, and oxygen on both sides of the equation. So this is balanced. It obeys the law of conservation of matter. All right. Now, the balanced equation for cellular respiration is simply the reverse of that. So instead of that, we have C6H12O6, okay, glucose, plus 6 molecules of oxygen yields 6 molecules of CO2 plus 6 molecules of water, H2O. Okay, and if you were to go through and count that again now, you would see that we still have 6 carbons on the left, 6 on the right, that's balanced. We have 12 hydrogens on the left, 12 on the right, that's balanced. And we have 18 oxygens on the left, 18 oxygens on the right. All right, and so what we just did, counting the atoms, is what number 6 is wanting you to do. So you can go through and say, okay, in the reactant side to the left of the arrow, how many carbons do we have? 6. Okay, on the products, how many do we have? 6. Hydrogen, we have 12 and 12. Oxygen, we have 18 and 18. And if you're ever balancing an equation and these numbers are different, then it's not balanced, okay? Because in order to obey the law of conservation of matter, you have to have the same number of each atom on both sides. And because cellular respiration is just the reverse of photosynthesis, as far as the equation goes, these numbers should be the same for cellular respiration. There we go. All right, number 7, how is it possible that the reactants and products from both chemical equations have the same quantity of carbon, hydrogen, and oxygen atoms, yet the reactants and products are different molecules? So the molecules contain the same kinds of atoms, but they're just arranged differently in the reactants versus in the products. All right, number 8, let's take a look. It says, what conclusion can be drawn about the relationship of the two reactions? We've kind of been focusing on this for a while now. The relationship between cellular respiration and photosynthesis is that their chemical equations are just swapped. They're backwards, okay? The reactants for cellular respiration are the products for photosynthesis. And the products for photosynthesis, The products of cellular respiration are the reactants for photosynthesis, okay? So the reactants and products are opposite of each other, okay? Number 9, describe what role energy plays in each equation. Okay, something we did not put in the balanced equation because it's technically not a chemical is energy. So energy is going into photosynthesis. So technically energy would be in the reactants for photosynthesis. It's absorbing sunlight. Okay, for cellular respiration, energy would be coming out of the reaction in the products, and chemical energy in the form of ATP in our cells. That's the whole purpose of us breaking down this glucose, is to get energy as a product for our cells to use, okay? And number 10, what is the purpose of photosynthesis and cellular respiration in terms of energy for an organism? So photosynthesis is capturing light energy, or another word for that is radiant energy, and storing it up as chemical energy in the form of glucose, okay? Then cellular respiration is taking that chemical energy stored in the bonds of glucose, breaking it down and releasing that energy in the form of ATP, which is a form of energy that our cells can use to do cellular functions, okay? And so that's part 1 for you, okay? Hopefully I didn't go too fast. If I did, you can always rewind and go back. Part 2 and 3 have you model the reactants and products for photosynthesis and cellular respiration. So before I end the video, I just want to show you the program you're going to use to model these. And it's called MolView. You've done it. You've used it before when we built the macromolecules. Hopefully today it'll be a little more simple because we're building only one macromolecule, would be glucose, depending on which reaction we're talking about. But the other molecules are pretty simple to build. So what I've built for you here is actually the reactants, or the inputs for photosynthesis. Photosynthesis, what goes into it? We've got water and carbon dioxide. But remember the balanced equation. The balanced equation has 6 molecules of water. So I've built 6 H2O, see that? 6 of these, and 6 molecules of carbon dioxide. So here's all 6 of these. So what you're going to do is you're going to build these when it asks you to build them. You're going to build however many you need from the balanced chemical equation. So like we needed 6 of each of these. You're going to click 2D to 3D, and it's going to generate a 3D model of the reactants and products that you're making. So here you can see the 6 molecules of water, 6 molecules of carbon dioxide, and then you're going to screenshot this and copy and paste your screenshot where it asks you to into these boxes, okay? Now, I know what you're thinking. You may be thinking, well, how in the world am I supposed to know what these molecules look like in the first place? Well, I've got a tool to help you out. Here is a reference sheet, okay? You're going to get a copy of this, and when you click on it, it will open up a PDF that has basically what the 3D model should look like. It's color coded, so you've got carbon, hydrogen, and oxygen. Carbon being black, oxygen red, hydrogen will be white, and it shows you what the structures look like so that you can go and build them in here. Okay? If you guys are confused by any of this or need any further help, feel free to email me. Okay? Good luck.